Okay, hello everyone. Welcome to Flink Forward Asia. My name is Shui Qiang, and I'm a big data engineer from TikTok. And today I would like to share our experience of building a unified lakehouse for large-scale recommendation system with Apache Paimon. And my sharing consists of the following four parts. First, I will introduce the development of TikTok recommendation model architecture, and then explain the need for a unified lakehouse in large recommendation model paradigm. And next, I will show the implementation of the user behavior sequence feature lakehouse and the user level training sample lakehouse with Apache Paimon. And let's begin with the development of the TikTok recommendation model architecture. And the recommendation system plays an important role in TikTok ecosystem as it tailors personalized content streams to provide a better user experience and keeps users engaged longer. And over the past decade, we have developed deep learning-based recommendation model with the combination of deep learning technology and recommendation scenarios. It mainly based on a large number of sparse and dense input features and a large-scale high-dimensional embedding layer. But this model has some limitations as it heavily relies on complex human feature engineering. And the sparse and dense feature also lose sequential information that can reflect the change of user interests. So inspired by the success of the large language model in various fields, we try to scale up the model parameters with more comprehensive user behavior sequence features and develop new models like large-scale recommendation model and generative recommendation model and the multimodal recommendation model. This model simplified the manual feature engineering and shift to a paradigm that center on user behavior sequences and have become the mainstreams in TikTok recommendation systems. And next, let's see why we need a unified lakehouse in large recommendation model paradigm. The large recommendation model gained good benefits in many business lines in the past 2 years. But behind the success, there are some pain points throughout the user behavior sequence feature production. From the business perspective, business teams build their feature production pipelines individually with different schemas that cannot be reused by each other. And the repeated development also leads to waste of time and resources that it usually takes several days to collect data from different scenarios and prepare resources for the pipeline execution. And from the architecture perspective, there are operational maintenance difficulties introduced by diverse components in the traditional Lambda architecture. And it may also cause data inconsistency from the separated string and batch pipeline. So to solve these pain points, we decided to build a general user behavior data asset. It's a lakehouse that can cover and be shared by all genres, scenarios, and business in TikTok ecosystem. It tracks the lifelong user behavior with a general schema, and a time range spans from hourly, daily, to monthly, even yearly. And it should also be a string and batch unified storage that provides real-time and batch analysis consistency. And Apache Paimon is well known as a streaming lakehouse with unified storage and high query performance. And it also provides transitional guarantee and EZ1 schematic for both string and batch processing. And it also has a rich ecosystem that will support for computing engine like Flink and Spark and compatible with other lake formats like Iceberg. So we choose Paimon to be the unified storage of the user behavior lakehouse. And the user behavior lakehouse is divided into 4 layers. From bottom to the top is DIN layer, DW layer, and DWS layer, and ADS layer. The DIN layer retains item features produced by feature engines for dimensional query, and including static item features and dynamic item features. And DW layer is a white table constructed from user behavior raw data and DIN layer. And the DWS layer is also a white table with normalized the user behavior sequence features and the aggregate labels. And the ADS layer maintains user behavior long sequence feature filtered by different business needs. Next, let's see the implementation of the user behavior sequence feature, Lakehouse, with Apache Paimon. And this is the overall architecture of the Lakehouse pipeline. First is the DIN layer. The feature engine continuously produces the item features and push to online store for online serving. And there is a Flink CDC streaming pipeline that captures the change of the feature values and write into a payment table that stores all versions of the features. And the multi-version feature will also be used for feature backfilling and cold start by PIT drawing on user behavior features on other layers. And next is the DW layer. We run a streaming ETL job to do some basic transformations on user behavior actions reported from different applications. And such as filtering and deduplication and setting default values for empty fields and value normalization. And then look up the dimensional features from DIN layer to construct a white row, a user behavior white row, and write into a payment table. And this is a primary key table partitioned by date and hour and bucket by user ID. And next is the DWS layer. It's responsible for label calculation based on the user behavior features in DW layer. We can define flexible window strategy and aggregate functions to calculate feature labels for different needs. And the last is the ADS layer. It served as a materialized view from the user behavior features in DWS layer processed by the string ETL job. And the features are pushed to online store by a streaming ETL job and backloaded to offline store by a daily scheduled batch job. We can see the pipeline is simplified with only a few components. That Spark, Flink and Spark as the computer engine, and Paimon as the unified storage. And there are some optimizations for the Lakehouse pipeline. First, we set the checkpoint interval of the Flink job to 1 minute to improve the data freshness for downstream pipelines. And we also make the payment writer to perform write-only action to get a high writing throughput, and run dedicated compaction job to periodically compact the files to avoid producing too many small files. And we also set up partition markdown listeners to ensure the data completeness for the batch job scheduling, that the batch job can only be executed when corresponding partitions has been marked success. And with all these efforts, we finally built up a batch and string unified payment lakehouse and a minute level end-to-end latency. It's capable of handling 6 million queries per second and writing 4 terabytes for an hourly partition. And then business teams can share and produce user behavior features based on this unified lakehouse and the general pipeline. And the time cost to build a sequence feature production pipeline reduced from days to hours. And then let's see a batch processing scenario. User behavior sequence feature backfilling and cold start is a key process for offline model research. It requires to apply point-in-time data to avoid feature leakage that might affect model accuracy, such as using future data to predict PAX events. So we need to keep all versions of the features that changes over time. And during the feature production, there is a Flink CDC streaming job that captures the feature changes and write into a payment table that stores all versions of the features. It's a primary key table, key by item ID and version ID, partitioned by date and hour, and bucket by item ID. And then we produce the user behavior feature for backfilling and cold start with a Spark job by PIT drawing on the user behavior table and the multi-version feature table. Oh, by the way, the Flink CDC pipeline will also detect the schema change of the features and automatically perform schema evolution without interrupting the task manually. And to support the PIT join, we designed a SQL function called PIT config to configure the join conditions, such as the time field of the left and right table, and the max allowed time differences between 2 items. and implement the corresponding optimized rules and strategies to translate the sparse cycle into a physical plan. Okay, and during the runtime, the user behavior table and the multi-version feature table are loaded by payment scanned, and then sorted by join keys and timestamp field, and then shuffled to a join operator to perform an early start soft merge join, and then finally produce the versioned user behavior feature. We know that data in payment is sorted by primary keys when it was returned, so the sort and shuffle stage in the runtime can be eliminated. That the same bucket of the user behavior table and multi-version feature table can be loaded by the same payment scan and then directly perform a sub-merge join. And this will greatly improve the join efficiency. It takes about 5 hours to process 600 terabytes of the user behavior sequence feature for 27 days. And next, let's see the user-level training sample lake with Apache Paimon. In deep learning recommendation model paradigm, it's commonly used point-wise sample to do model training. It treats each user item interaction independently and identified by item ID and user ID. And it might cause redundant storage for the same user features during the model training runtime. And however, in the large recommendation model paradigm, the listwise sample considers a full list of items grouped by user ID. The compacted sample list will also bring a higher storage efficiency during the training runtime. So we develop a user-level training sample engine to transform the point-wise sample and to a list-wise sample for the large recommendation model training. And it's a Flink streaming job. At the beginning, we build up the training sample pipeline with Flink embedded state backend. That the point-wise sample are collected by a window operator and grouped by user ID, and the window state is stored in the local RocksDB state backend. And when the window is triggered, the collected sample list will retrieve from the RocksDB state backend and emit to next operator to finally build up a listwise sample. The window is triggered when 500 samples for the same user are collected, or the 12 hours long timer is fired. And a point-wise sample, the size of the point-wise sample is about 50 kilobytes, and the sample value field takes out the majority of the size. And as the job keeps running for a long time, the total state size grows up to 5 terabytes to 1 petabytes. And the task stability is compromised by the large state, such as taking a long time to finish a checkpoint or recover from a failure restart. So we changed to use a disaggregated remote state backend that the collected sample state, the large sample state stored in the remote state backend on HDFS, and the local RocksDB state backend used as a local cache. When timer is triggered, when window is triggered, it will firstly retrieve the collected sample list from local RocksDB state backend. If it does not exist, it will try to retrieve from the remote state backend. The disaggregated remote state backend successfully alleviates the overwhelming state pressure, but it still has some limitations, such as the state cannot be reused by other jobs, and it's a black box that cannot be queried. And the short state TTL also limits the long-term analysis. So finally, we decided to build a sample lake with Paimon and build up a training sample pipeline with Paimon bucket shuffle lookup join. The point-wise sample are written into Paimon as a sample lake, and it's a primary key partitioned by date and hour and bucket by user ID. And there is another streaming job that continues consuming the sample lake, but only the primary key fields are selected, filtering out the large sample value field. And the primary keys are collected by the window state grouped by user ID. And since only the primary key fields are collected, so the window state will be very small. It's about 300 gigabytes. So it will not bring high pressure for the state storage. And when the window is triggered, the collected primary key will be emitted to a next operator to look up the sample lake to retrieve the sample value field and finally get the complete point-wise sample and finally build up a list-wise sample. Here we apply the Paimon bucket shuffle strategy to improve the lookup performance. That the UIDs that assigned to the same bucket will be shuffled to and processed by the same operator. And the join operator will build up a local query table for a specific bucket. And when look up the sample value, it will first look up the files in the local query table. If the file does not exist, it will try to download the corresponding bucket file from HDFS and try look up again. So gradually, all files of the bucket will be downloaded to local disk, and the lookup efficiency based on local files will be greatly improved. And there are some optimizations for the training sample pipeline. First, we can see the time window spans 12 hours long, so we can build up the local query table for some unchanged partitions early before the window is triggered to avoid downloading too many files due to a large number of timers triggered in a short time. It's about 10 terabytes for an hourly partition and 2 gigabytes for a bucket. So it will not bring high brain pressures to the local disk storage. And we also support look up local files and download bucket files asynchronously to improve the throughput. And finally, we build up a batch and stream unified sample lake, can be used for real-time and also batch sample production. And we also implement low latency and high throughput training sample pipeline with Paimon bucket shuffle lookup join. Okay, let's talk about the future plan. And first, we are going to integrate Paimon with table service such as Apache Flux to provide a sub-second end-to-end latency. We can see that the end-to-end pipeline is only mini-level currently. And the second is to improve the ad hoc query performance by integrating Paimon with a disaggregated KV storage query engine, so that the data in Paimon can also be used for online serving. And finally, implement one unified storage covering all usage scenarios. And that's all for my sharing today. Thank you for watching. Okay, do you have any question?
Okay, I have one question about
okay.
You told the schema chat, but it's not the highlights of how you can handle that.
Okay. I see. There is the schema change detection operator to detect the change of schema, and then since there is many subtasks, we also run a coordinator to collect the schema change event and align to all subtasks. Only when all subtasks detect the schema change, then the schema change detection coordinator will return an event that we can begin to schema evolution. Then the real schema evolution is performed by the schema operator in the Flink CDC pipeline. Because now currently the Flink CDC pipeline does not support distributed schema evolution. So we manually detect the schema change, and first to align the schema change annul the detection, and then finally emit the schema change event to the schema operator.
But it need to be restart
No need to restart.
on fly, right?
Yes.